So let's begin. So oh, wait, hold on. Why does it not? Let me see. All right. So the voice okay, right? If the sound doesn't come through, let me know. So today, right, we'll start lecture 3. But in terms of the materials, we are sort of done, right, or beyond probability review. Okay, like math probability theory review, we're done with that. So, well, even though we're still not doing stochastic processes exactly yet, the materials here, right, roughly correspond. Well, not roughly, but will be like you can find it at the end of chapter 2, beginning of chapter 3. Okay, in the textbook. So we're beyond probability theory, right? The review material, preparing to go into stochastic processes. What that means is like these materials will be new, right, to hopefully all of you, and so pay extra attention, right? In terms of the difficulties, it's actually going to be harder than the ones we've been discussing last week. All right. So the topic, right, of this lecture is still about, well, actually not still about, but will not be just about random variables in general, right, but about sum of random variables. Okay, so especially, you know, the topic of sum of IID random variables. And also, right, we'll move to the case when random variables, right, they are not independent. What we'll still look at the sum of the random variables, because, you know, there are examples where, you know, we look at, let's say, components of a stochastic process or whatever the reason is that we sum things up, but they're not independent. Okay, but a lot of times these are what we'll be looking at. Also, right, another possible violation, right? So IID, of course, is independent, right? Identically distributed, right? Distribution. So either one of these assumptions can be violated, right, in the sum. So of course, the easiest case is this, but you can have identical. Well, you can have independent sum but not identical, or you can have sums that are not identical, are not independent. Okay, we'll see. So just to remind you, right, the kind of like the benefit, right, or sort of like the classical result, right, of sum of independent random variables is that if you sum, right, independent binomials, then you get a binomial distribution. And notice, right, the requirement here is that the two success probability must be the same. Okay. So this actually, right, we saw that when we say that the sum of the Bernoullis, right, sum of n IID Bernoullis will give you a independent, well, sum of IID Bernoullis will give you a binomial distribution. Another result, right, is that if you sum IID geometric, then you get a negative binomial. Okay, so it's pretty easy to see why this is true, right, by just looking at what this means, right? For example, a binomial counts the number of successes, right, in the in so many trials. So basically, right, you can look at this as the group of first N1 trials, right? First N1 trials, and you count how many successes, and this is the second N2 trials, right? And you count how many successes. So if you sum them up, you get the total number of successes in this number of trials. Geometric is the same, right? It's the number of trials until you see the first success. And the negative binomial, right, is the number of trials until you see the nth success. So basically, right, if you sum the number of trials until for each success, right, n times, you get a number of trials until the nth successes. Okay. And right, the whole point, right, is not that we just want to establish these connections, but they are helpful, right, for us to drive the connection between, right, the expectation and variance of a binomial with expectation and variance of a Bernoulli, right? remember that this is easier, right, to calculate the expectation and variance of a Bernoulli, but it's not that easy, right, to calculate the expectation and variance of a binomial using definition. So using the sum, right, formula, that is, right, expectation of the sum, right, is a sum of expectation, and variance of the sum, right, is a sum of the variance. The second one, right, requires that they are independent. The first one's always true, but using these two, right, results, then you can, right, establish the expectation, let's say, right, of the more complex random variable, right, using the expectation and variance, right, of the more complex random variable using the expectation and variance, right, of the simpler random variable. Same deal, right, with the negative binomial. So we talked about this before, right? So this, right, is new, new-ish, right? So we haven't talked about this as much in the previous lecture, but it's also true, right, that if you sum independent Poissons, you get a Poisson random variable back, okay? But here, right, the parameters add, okay? And note that it's actually kind of consistent because, right, if you have a Poisson, right, then expectation of a Poisson random variable, right, is lambda. And the variance of the Poisson is also lambda, right? Therefore, expectation of the sum, right, is a sum of the expectation, which is lambda 1 plus lambda 2, right? Here, which is the parameter, right, of the Poisson. And the variance also works in the same way, so it's consistent. And this, right, will be useful in the context of the Poisson process, as you will see later. But basically, right, a Poisson process counts a number of arrivals, okay? The number of arrivals during some time interval starting from 0, right? And let's say S and let's say T, right? So it makes sense, for example, right, that basically, say from 0 to S, you have a number of arrivals, right? And that would work as lambda times S in terms of the rate, right here, okay? So the average of customers arriving, right, in that time interval 0 to S is lambda times S. But of course, right, the actual number, right, the actual number of arrivals, which is denoted by n sub S, is a random variable, right? Is a random variable, okay? Is a Poisson random variable with this rate. Similarly here, right, the average number of customers arriving here is lambda times T minus S. But the actual, right, the actual number of arrivals, well, so N, right, as the random process here, as the Poisson process, keeps track of how many, right, events have happened by that time. So NT minus NS, you see, right, represents the number of arrivals between the time interval S to T, right? So this we're explaining, right, in the language of modeling, but in the language of, let's say, random processes, what we're looking at is the so-called increment, okay? This is the increment of the Poisson process from S to T. This is the increment of the Poisson process from 0 to S, okay? And of course, I mean, it sounds like a truism that if you add these two, right? If you add the number of arrivals here plus the number of arrival here, right? You get the total number of arrivals, okay? So that sounds like a truism, but the math behind it must also try to be consistent. That is, right, if this is a Poisson random variable, this is a Poisson random variable, you kind of want the whole process to be a Poisson random variable as well. So, okay, notice, so this is Poisson lambda T minus S, and then Poisson lambda S. If you follow the result of the sum of Poisson distribution, you get a Poisson lambda times T, which is the total number of arrivals from 0 to T, right? So that's the foundation of the building block of a Poisson process. We're not discussing the Poisson process right now, But what I'm trying to point out, right, is that behind, right, the whole connection of how Poisson process works is the idea of, or the result of summing, right, independent Poisson random variables. Or, right, as you can see, the theme is sum of independent random variables in general. And you see, right, in the Poisson case that I just talked about here, the identical part, right, is taken away because, right, here you have, you know, Poisson lambda 1, Poisson lambda 2, so that they're not identical, but they're still independent, right? There's also a corresponding result, right, with the normal distribution. So again, right, if you sum independent normals, you get you get a normal back. But note how the parameters work, right? The mean at and the variance at, okay? And again, this is super important that we keep track of what we mean, right, by this parameter. This is the variance, right? So the variance, sigma 1 square plus sigma 2 square, right? Because this is independent. These are the individual variances add up to the variance of the sum, right? If it's the standard deviation, it won't work that way. So the analysis is the same, or the meaning is the same, right? But now it has to do with Brownian motion, which, right, is the position of a particle, right, moving, let's say, a long time, right? So this is the Brownian motion tracking, right, the position of the random variable, okay, across, the position of a particle across time. So Ws, right, is the displacement, right, of the particle from time 0 to time s, and Wt minus Ws is the displacement, let's say it moves down here, right, the displacement of the random variable, right, from time s to time t, right. Wt minus Ws is negative here, right, the Brownian motion has moved down. But if you add them together, right, then you should get the total displacement from time 0 to time t. And it should be consistent in the sense that the distribution, right, of the displacement, I mean, not that it should, but it'll be very nice, right, for the displacement, the distribution of displacement to be consistent throughout. So if you have the normal distribution there, right, then you sum independent normals, you get a normal back. And so, right, that's the backbone of how, let's say, the Brownian motion work in terms of the distribution of its increment. Right, again, right, behind it is the result of summing independent random variables. Any questions so far? All right. So we're just gonna mention quickly, right, the proof of the previous slide. So notice, right, when we looked at the binomial example or the geometric example here, right, the proof is by definitions of the random variables. What we mean by this is like the proof is by what the random variable is supposed to model, right? It models the number of trials or number until like the first success, right? Or the total number of successes in n trials. With the case of the Poisson, right? Or with the case of the normal, that's less clear. Sure, right? The Poisson models a number of arrivals, right, in a time interval. But I don't think, right, within that context or within that definition, why you sum two Poissons, right, two independent Poissons, you should get a Poisson back. Or, right, while you sum two independent normals, you should get a normal back. So the mathematical tool, right, behind to establishing that formally is the moment-Jain functions. So we're not doing probability theory exactly in this class, so we're not going to harp on the things that we don't need for stochastic processes, okay? So all the materials I emphasized on are materials that kind of like will be useful for stochastic processes. The ones that sort of like in the background but are not super necessary, we're going to mention it just in case we have to mention it again, right? But we're not going to like go into the details. So moment-Jain functions is such a kind of concept, right? But it's actually super useful throughout, like basically probability theory. So basically, right, the moment-Jain function defined as expectation of, e to a tx like this defines, right, the distribution itself. Meaning that, right, if you know what the MGF is, then you can tell what the random variable is. And right, why the MGF is useful when you have the sum of independent random variables. Because if you have independent random variables, then the MGF of the sum is a product of the MGF. Okay, let's see how that works. So here, right, the MGF of the sum will be, right, by definition, expectation of e to a t x1 plus x2. Okay, but the exponential, right, splits, right? So you got, this is equal to expectation of e to t x1 times e to t x2, right? But now you use independence, right, of x1 and x2 to now split the expectation. Okay. And so, right, why this is useful? This is useful because if you know, right, the individual MGFs of x1 and x2, you will know the MGF of the sum, right, by taking the product of the individual MGFs. So again, right, this is why sum of independent random variables are quite a popular topic, right, in probability, because you have the MGF technique to handle it kind of efficiently. And so, right, for Poisson random variable, then, right, a Poisson random variable, you can prove that its MGF is like this. So now, right, apply this result to combine these two results, right? You see that the MGF of the sum of two Poissons, right? If you have Poisson lambda 1 and Poisson lambda 2, right? Then the MGF will be e to lambda 1 t minus 1, right? And e to lambda 2 t minus 1. Oh, sorry, not t, e to t minus 1. Right? And we multiply them, right? Because the MGF of the sum is a product of the MGF. But notice if you multiply this exponential, you get e to lambda 1 plus lambda 2, e to t minus 1. And right, this looks exactly like the MGF of a Poisson. But now, right, the parameter is lambda 1 plus lambda 2. That's why we can conclude that the sum of independent Poissons is a Poisson with that parameter. Right? Any question about the sum of Poissons, sum of independent Poissons? Okay. So for the normals, right, it works the same way, but now, right, we need to use the MGF of the normal. So, well, let me write on a separate paper, right? You know what? Let me erase this. Okay. So now, right, we will look at e to t, right, mu1 plus t square sigma 1 square over 2, right? That would be the MGF of a normal mu1 sigma 1 square, right? And the MGF of a normal mu2 sigma 2 square will be e to t mu2 plus t square sigma 2 square over 2, right? And we multiply these two together again. And so, right, of course, when you multiply these together, you get e to t times mu1 plus mu2, and then plus t over 2 times sigma 1 squared plus sigma 2 squared. But then again, right, you see that match exactly, right, the MGF of a normal with, right, mu being mu1 plus mu2, sigma squared being sigma 1 squared plus 2 squared. So, right, we get that result. Okay, any question? All right. So, let me see. In terms of problems, is there any? Okay. So in terms of, those, right, these are, I guess, well, so these are still maybe, right, not standard materials, but like materials you might have seen, right, in 477, right, in probability theory so far. This one right here, right, exactly is the one that I meant to be the new material. Okay. So the idea, right, so far is, you see, we analyze, right, we have a random variable, and we analyze, right, how it is a sum of all the random variables, right, independent, and then we exploit that fact, right, to prove something about the x, right? But sort of like in all this discussion before, right, up to now, the xi somehow are given to you, right? So in a way, you kind of go from here to here, right? You go from the sum, right, the sum expression to the random variable, right? Note that we conclude sum of Poisson is Poisson, sum of normal is normal, right? Sum of geometric is negative binomial, and so on, right? We go from the sum to the random variable. What we're doing now is to go back. We have a random variable x. We want to somehow be able to express it as a sum. Okay. When dealing with a complicated random variable x, we want to represent it as a sum of simpler random variables. Okay. The techniques is the same. The theory is the same, but the direction is reversed, or rather the challenge, right? The challenge is to somehow be able to answer this question. Right? I have a complicated random variable, right? I want to express it as sum of simpler random variables. Well, what are they? Can I find them? Okay. And again, right, the advantage is that, right, once you are able to express it as a sum, then expectation and variance, which are usually the question we'll be asking, will be quite simple. Because, expectation of sum, right, is some expectation, variance of sum is, sum of the variance, and so on. Okay. So that's the theme, right, of this lecture, rather, or this problem set, that given a random variable, how can you express it as a sum of simpler random variables? What are those random variables? How can we find them? Okay. So here, right, is the general result I told you before, right? That if you have just a sum, then the point of this result is always true. Okay. Now, of course, if xi and xj are independent, then the covariance, right, will be 0. And so, right, if you know that these are also independent, then you can drop this. But, right, watch out in general, because when you express, right, a random variable as a sum, it may or may not be the case, right, that the random variables are independent. So you will see an example real soon, right? So you do not want to use the special, right, formula without checking that they're independent. Okay. Any questions so far? All right. So maybe well, let's this is the result, right? So let me kind of give an example, right? Because I don't want to spoil the result, and I want to discuss it. So remember the hat problem, right? I told you that this hat problem is kind of like a model problem that we keep going back to because it has a lot of ideas. So you have n persons, right? Throw the hat right into a pile and pick the hat right out at random. Okay. Remember, right, we let the random variable x, for example, be the number of people, right, or persons with the right hat, right? And when we deal, right, when we dealt with the inclusion exclusion formula before, right, in problem set 1, right, what we did is we found probability x equal to 0, okay, which is, right, an expression. I mean, I'll write down, right, if you so if I remember correctly, it starts with 1 over 2 factorial, right, minus 1 over 3 factorial plus 1 over 4 factorial, right, and so on, right, until minus 1 to the n, right, over 1 over n factorial. Okay? So, right, remember, right, even this result by itself takes some time, right, to write down, to establish it correctly, right, using, you know, EI, right, the event that person I, person J get their right hat. Now, what we want, right, the question for this lecture is something like this: find expectation of x. Okay, find the average number of men with the right hat, or find the average number of persons with the right hat. All right, and that's a challenge here. So I'm gonna pause here, right, to let you appreciate, right, this problem a little bit, and kind of like let you think about this problem, right, and see how it's difficult and how to, or what we can proceed, right, to do here. Again, right, the theme of this whole lecture, this entire lecture, is sum of random variables, right? Sum of random variables, and expressing a complex random variable as sum of simpler random variables, so that we can exploit that sum to find expectation and variance. Okay, so given that theme, right, and this problem within that theme, see if you can think of a way to proceed to solving, right, this question. All right, any input, any idea, any suggestion?
One idea, but I'm not sure if it's correct.
Go for it.
You theoretically represent x1 to n as Bernoulli's, where 1 is getting the hat and 0 is not.
Fantastic. That is the right idea, right? So the whole point, right, and the key here is, as you just mentioned, the theme is something called indicator function or indicator random variable, which is also a Bernoulli random variable. So remember, right, a Bernoulli takes on value 1 or 0, right? So that's exactly indicating, right? So what do we indicate? And that's exactly the key, right? You want, I mean, not always, but sort of. So here, right, notice x is a counting random variable, isn't it? It count the number of people with their right hats, right? And how do you count? Very simple. You go through the first one, you count, does that person get their right hat or not? And then the second, right? And you can put your finger up, right? When do you put your finger up? You put your finger up when, right, the person gets their right hat, right? That's how you count. So symbolically, then, you let xi be 1 if the ith person, right, gets their right hat, and 0 if not. Then the count of the total number, right? This is also, there's a word total here that's implicit, will be the sum of xi. And really, right, this is the entire theme of this lecture. you see problem after problem with this theme. So that's a challenge, right? You have to be able to find the xi's. So I want to pause here to see if there's any question about the connection before we now proceed to solve this. Okay. So, right, now let me mention something, right? A Bernoulli, remember, right? A Bernoulli P, then its expectation, right, is P, right? Which, by the way, is probability x equals to 1, right? So if you have xi, let's say, right? So basically, expectation of an indicator random variable is exactly the same, right, as the probability of the success. And that's why it's easy, right? But here's, sorry, this is wrong, right? Not expectation of x. X is equal to a sum, okay? So the question was expectation of x equals to whatever. And right, we will express x as a sum. Then, right, expectation of x will be the sum of expectation, right? But what is each xi? Xi is the indicator function of the ith person gets their right hat, right? So that will be the sum of what then? The sum of the probability, right, of the ith person gets their right hat, isn't it? And what's the probability that the ith person gets their right hat? 1 over n, right? So the answer is 1. All right. Any question about this?
I know so the last equality sign, it's the sum of the expectations of the xi's, right? Technically, it's equal to the sum of 1 times the probability the ith person gets the right hat plus 0 times the probability the ith person does not get the right hat, right?
But still, you see, I
Yeah,
cut
of
through it
course.
by saying expectation of Bernoulli speed. Yeah.
Oh,
So
okay.
yeah, you're absolutely right. But if you do it for like 5 times, you get tired of the 0. So you just
Yeah.
move into a 1. Does
Yeah.
that make sense? No, it's fine, right? When you're new to this, I saw that your approach is very systematic, and that's great. Nothing wrong with that. If that's what you're comfortable with, go for it,
Oh,
right?
no. I just wanted to review, that's all. Thank you.
No, that's fine. Right. But no, what I'm saying is like eventually you will drop it like I do. Or another way I want to say is I do have the habit of cutting through the materials quite quick, which might leave some students hanging. So if you have a question, do ask, right? But your approach is perfectly fine, right? But eventually you will drop it very quickly like I do. Yeah.
Sure, thank you.
Yep. All right. Any question? Any other question?
Yeah, I actually have one question is what makes the Bernoullis independent? Because if the probability is 1 over n,
Fantastic. Have I ever said the Bernoullis are independent here? Did I ever say that? Fantastic question. But notice I never said that, right? But do I need it so far? The answer is no, because this is always true. See the beauty of that? Your question, which is a very good question, will be relevant when I compute the variance of x, or if I want to compute the variance of x, right? Because the variance of x, in this case, right, is not the sum of the variance of xi. Because, right, the action of the ith and the jth man are not independent. Okay? So we can still do it. We can still do this problem, and it's not too difficult. But I choose to not do it eventually in my career of teaching this course because it's just a bit tedious. But you can look into the textbook. This is where you can look it up if you want, right? I don't think it's It's okay. It's actually quite nice. But what you have to do now is to deal with the covariance term. Okay, for this problem. But notice if we're just happy or content with calculating the expectation, then the interaction of xi's are immaterial here. Is that okay? And exactly that exactly is why, right? When I say the sum, they may or may not be independent, and we need to be mindful that these are not independent. But what I've been doing so far, I'm okay. All right. Any other question? All right. So, right, like I said, there is, right, the next layer where you calculate the variance. I choose to skip that because, you know, there are a lot of things to go through in this course. But do look it up, right, if you're interested in this kind of direction more, right? It's a nice calculation. It's not that difficult. And I think it's shown in the textbook. All right, so here, right, this is exactly sort of what I just went over with you, right? But instead of using xi, I use the indicator notation. Doesn't matter. Oh, you know what? Well, I did show you here in the slide. So okay, fine, right? So here, let's go through it then, right? We're not gonna ask the questions, but so here's a variance formula, right? So the variance of the Bernoulli is P1 minus P, right? So that's this term right here. Remember, P is 1 over n, right? All right. And the usually, right, when you deal with the variance of the sum, right, then and if they're not independent, then the covariance is the more complex terms you have to deal with. All right. So how do we do a covariance calculation? So we for the covariance calculation, we just use definition, right? Expectation of the covariance is going to be expectation of the product minus the product of expectation. And right, these are easy because each of them is 1 over n, so it's 1 over n squared. Let's explain this, right? Now, so one thing you want to note, right, is the product of indicator, right? If you multiply two indicator functions, you get the indicator of the joint or the intersection, right? Why is that true? Notice, right, xi times xj, right, is only 1 if, right, xi and xj is equal to 1, right? And 0 otherwise, correct? So if you multiply two indicator functions, you get the indicator of their and. Is that okay? And so you also get an indicator back. But this is an indicator function of the ith person and the jth person getting the right hat. So remember, we did that before as well, right? 1 over n times n minus 1. All right. And then, of course, right, this goes into here. And that's your final answer, right? I mean, oh, you know what? So again, right, I think I exaggerate the ugliness of this calculation. If you plug it in and you simplify, you do get 1. So it's actually a nice calculation. Anyway, right? But here, I just want to focus on expectation calculation. Variance, as you can see, right, takes a little bit more time. So I'll show you to here, right, for completeness, but focus will be more on expectation calculation.
Can you scroll up to the variance formula?
Sure, the variance formula. All right.
You just scroll
Oh,
past it.
Oh, you mean the covariance formula?
That one. Yeah.
Yeah, yeah, okay,
Thanks.
sure. Yeah. right, are we okay? Any question about this? All right. So, for whatever reason, right? Let's say coupon problem. There are many types in ROS, right? In our textbook, is a, let's say, a popular type of question or popular way to ask question. All right. And let's, so especially is very amenable to indicator function approach. So first of all, what is coupon, right? Coupon, you know, if you want, right, it just really refers to type. So if you find the word coupon a bit hard to digest, that's the word from the textbook, you know, refer to types, okay? So let's take a look at there, like I said, there'll be tons of coupon problems, right? We'll be looking at. And like I said, right, even though the notion sounds a little bit bizarre, right? Why do we care about coupons? It's really about types. So, you know, when you look at it like that, right, that this question is quite general in the sense that it's helpful, right, to when you have to consider, right, events or outcomes of many types. All right, so here's a question, right? So there are n types of coupon. All right, so basically, right, there are n types, right? There are n categories of outcome, and each, right, independently appear with probability pi. So of course, right, the sum of the pi, right, I from 1 to n is equal to 1, right? And this, of course, should remind you of like the multinomial multinomial random variable, right? So each outcome, right, each coupon, right, has n types, or how to say this, right? So basically, right here, right? Let's look at this. We aim to find the expected number of different coupon types in a sample of k coupons. So let me refer this. Let me recast this, right? In a more let's say familiar example, and you'll see, right? And I like to cast this sometimes in the we already talk about blood types, right? That's one way you can do it. But I also, let's do measures, right? So, you know, let's say student in this class, right? Will have different measures, right? You know, CS, math, I don't know, business, right? And, you know, for sake of simplicity, right? Let's say everyone has only one major, right? Math, CS, right? And of course, right, if you take a student in randomly, right, they can be a math student with some probability, right? CS student with some probability, business student with some probability, or statistics student, right, with some probability, all right? Let's say that like there are only 5 different majors possible, right, that takes this class. Again, right, that's probably not true, but let's say that. And let's say, right, I don't know, right now, I think this class has like 15 students or so, right? All right, but of course, you know, each student, right, randomly is of a major, right? It makes sense to ask, okay, how many different majors there are in this class? Does that make sense? Because, right, you know, all 5 majors, right, don't have to be present in this class, correct? It could be by chance that this class has only math student, for example. Is that okay? We will want to find the expected number of different majors in this class. Okay, so far? So, right, I mean, just for the sake of clarity, right? Because again, right here in the abstract notion, you know, the letters will be very confusing if you use the wrong letter, right? You will get the wrong result, right? So, okay, match for me here, right? 5 and 15. 5 here refers to N or K in the language here. Five refers to N or K.
N.
Correct, right? 5 refers to N, the number of types, and 15 refers to K. Are we okay? All right, good. Right, now let's proceed to solve this question. So again, right, let X be the number of different coupons, right? A number of different types in the collection. All right. The key to solving this question is to break it down to a sum of simpler random variables, an indicator, if you will, right? Again, you don't have to, right, break it down to indicator function, or you may not be able to. But the way these problems you'll be seeing is most of the time you break it down to indicator function. So what type of indicator function can we express X as the sum of? That's a key question. Here's another helpful question, right? A helpful thing you can think about when you solve this question. What do you go through? You go through what? There are two things you can go through, right? Because when you sum things up, you go through some list. But what list are you going through here? You can either go through the list of coupons in the collection, or you can go through the collection, the list of collection, or you can go through the collection, or you can go through the types, the list of types, right? In other words, you can sum over 1 to n, or you can sum over 1 to k, right? And when you think about it like that, you understand what I'm trying to say. Then one way to go through it makes sense to count, and the other way doesn't make sense. So see which way you want to go through.
If you sum over n, then you have to check for each value in that range from 1 to n, is it present in the collection or not? So it's a binary question for each value. Kind of like a
True.
Bernoulli.
No, it's always about, it's sort of a Bernoulli here, right? So that's sort of established here. But the question is, which list do we go through? Because if you'll see, right? If you go through the list of coupons in the collection, is that correct? Or if you go through the list of the types, is that correct? So you're saying that you want to go through the list of the collection, right?
Yeah, I mean, I guess you would parse through the sample, the
Okay,
collection.
let's look at the students, right, to make it concrete. So I will go through each student in this class, and what do you want to ask for each student? Whether what?
What major are they in, right? So
If you ask what major are they in, notice that's not a Bernoulli type of random variable, because
right.
there are 5 types, right? And notice that when you do that, the key word here is what? The key word here is different. Okay. When you go through each student, how do you keep track that you have seen that major before? Does that make sense? So you go through a first guy, let's say he's a math, whatever, right? And you go to a second guy. Okay, suppose he's a math again. So you don't count that extra, right? Because you want to only know the number of different majors. How would you do that?
Would it be easier to go through the list of types in that case because you're asking a more binary question?
Exactly. No, I'm exactly referring to that, right? Notice that here, right, we should go through a list of types. So in other words, right, we should go through the list of majors, right? And what question do we ask?
Is there a student in the collection with that major? Yes or no?
Exactly, right? Because if you, so let xi, right, be the indicator function that if the ith type is in the collection, and 0 if not, right? Because then if you sum up all the types, whether or not in the collection, so it's sum from 1 to n, then you get the total number of types in the collection, which is the number of different types. Do we agree? So that's right. This kind of analysis is the key to solving these kind of questions. Figuring out what the xi is, figuring out what the sum is, and doing it correctly. That's the challenge of all these problems. All right. Any question? Okay. So I think we're getting close to the quiz time. So we'll go back to this, right? After we finish the quiz and take a break. So we'll pause here. All right. So for the quiz for today will be the hat problem. Okay, and I'm just gonna ask for the expectation of x. All right, and again, right, I know I told you the number, try to show the whole work, okay? Express x as a sum of xi's, what are xi's, and then sum it up. Any question before we turn off the audio and video?
Just the expectation, not the variance, right?
No, just expectation, correct. Okay, and again, right, not a single number, but everything, all right, the whole work, okay? Okay, so we'll continue at 11:35, okay? Is there any question before we continue? Okay, so, right, so to continue with the question that we were doing. Basically, right, notice that in these kind of questions, the challenge, right, there are two challenges. The most difficult one, right, the most difficult one is to find the xi's. All right, I can tell you that that's the conceptual obstacle that you have to deal with for all of these problems. If you don't get it right, forget about solving anything else, right? Because your sum is either wrong, meaning it doesn't match what's supposed to, or, right, you get a quite complex xi to deal with. The second type is a bit more rare, meaning your sum is still correct, but you could have made an easier choice. But right here, definitely if you sum through the collection, then I think you'll get the wrong answer. Because, right, you need to get to the number of different types, right, rather than whatever, right? So you have to sum through the types, okay? But then that's the first one. The second, right, now once you suppose you identify this correctly, then you apply the formula, right? Which is expectation of x is a sum, right, of expectation of xi, which is a probable sum of the order probability xi equals to 1. But you still right now have to deal with the answer here, right, and find that out correctly, right? Because of course, if you write that probably wrong, then you get the whole answer wrong anyway. So let me pause here, right, and see if anyone has an input on for this particular question, right? What is probability xi equals to 1?
Are you asking this question in the context of our major question?
Yes, and I see that somehow my AirPod is not connecting. So let me see here.
And are we assuming that all of the majors are uniformly distributed across the 478 students?
Sorry, my AirPod was not connected before. All right, so yes and no, right? First of all, look at this, right? We could do it in this specific scenario just to get you familiar, but right, I mean, I think after we explain, right, 5 is n, 15 is k, right? There's no reason why we don't have to, right? We just solve it with n and k, right? Second, notice each time appears with probability pi. So I think it's not uniform, right? Each has their own probability. Let's say math is more rare or something like that. Is that okay? So math appears, let's say each student is a math major with probability 5%, something like that. Right, so what is probability xi equals to 1 here?
PI? Or do you expect a more nuanced answer?
Much more nuanced, because what is xi? Xi is not, right, indicator function that something is the ith type, right? What is xi in our definition?
There's at least one of somebody of that major.
Exactly. Excellent. Perfect. Right there. So it's not pi, right? So what is probably xi equals 1? Notice, right, the 1 here is the one of the indicator function, not the 1 in the count. So lots of things going on here, right? That's why I say the materials are not getting much more complex, right? It's not as easy as before. Well, the answer is any further input before I tell you the answer? So the last student, right, said it almost, I mean, kind of perfectly, right? There's at least one student of that major, right, in the collection or in the class. Well, how do you do that? Well, at least one means 1, 2, 3, 4, right? Up to 15, up to K. But that sounds complex, isn't it? Well, what can we do? We can count by or we can calculate the probability by the complement. Right? At least one is the same as 1 minus not present. Correct? So probability xi equals to 1 is 1 minus probability, right? That xi is not, or the ith type is not present, correct? In the collection. So here, right, actually, even though that's the definition, 1 minus p of xi equals to 0 is much easier to deal with. Because right now, do we see what probability xi equal to 0 is?
Like 1 minus pi to the k.
Perfect. Perfect. So, oh, sorry, there's a sum here, right? There you go. Right, because you have to go through each of the student in the class or each of the coupon and say this is not our PI, right? And they're independent, so you just multiply them out. So that's the solution. Okay, any question about this coupon problem? They said we'll have all other types of coupon problems, right? But coupon refers to that types of outcomes. And the challenge here is for you to identify the right indicator function, the right analysis that we just gone through. All right. Question? You know what? So there's the next topic of compound random variable. Oh, okay. Actually, right, it's not the next topic, as I said. We'll see it in the next lecture, right? But here, while we're at, right, I just want to advertise for, right? You might think, this is okay. Wow, this is complicated, right, and whatnot. The answer is no. We're not even there yet. The next level up, if you will, right, is instead of having a sum of ID random variables, we'll have going to be, you can call it a random sum, if you will, right? Where basically it's already random, right? But the random so far, right, comes from the summand, right? That term just summing up are random. But the how many of them you're summing, right, are constants, right? But you can have the case when how many you summing up can also be a random variable. Okay. You're like, wow, that's crazy, right? When would that happen? Well, it happens very naturally, right? Remember, right? Say this can be viewed as a random walk, right? Meaning that xi is the step size, and some from 1 to k is the position after k steps, right? So some up to n randomly, it's like you ask, okay, at a random time, right? With random step size, where will you be? Right. So you can ask, right, randomly at a certain time like that, right? A different clock, right? Let's say there's a particle move randomly, right, along the line. But then there's another clock, let's say that let's say the first time that you roll a 6 on a dice, right? That's another independent random variable. So by the time you get that 6, where will you be? Or what's the probability, right? What's your distribution along the line of the random walk? So anyway, right? Such an idea is called a compound random variable. Again, right, in the theme of what we're discussing right here, it basically takes the whole IID sum one level further, right? And that's exactly why, right, we have to do a lot of preparation before we do stochastic processes. Because all of these techniques, right, will be relevant when we deal with, right, chapter 4 and so forth. So this is advertising for future material.
So now let us move on to the problem set, right? And just fair warning, it'll just be, sum of random variables after sum of random variables in this problem set, all right? And they may or may not be indicator function, may or may not be. But
Professor?
the check. Yeah, but
I think your screen might be frozen.
oh, is it? Okay. Let me yes, absolutely. Sorry. Was it frozen at the slide before?
It was frozen at the slide. It still is at expressing a random variable as a sum, the coupon collection problem.
Oh, okay. Yeah, thank you. Definitely let me know. So sorry. So I guess you did not see this slide. Right? I was talking about this slide as a solution.
No,
you
we
see the
didn't see
slide?
this one.
Okay, cool. Yep, so sorry. So I was talking about this, right? And then, okay, let me show you this. This is basically the answer to what I was talking about, right? So I'll pause you for like 30 seconds for you to see it if you need to. Okay. And then, right, the last slide is here, where I was expressing, that notion of summing, right, random variables, but the upper limit is also a random variable. So it's just advertising, right, for the next material. So apologize for, I don't know, the technical age. If it happens, definitely tell me before that even, right? Are we okay? All right, great. So yeah. So right, the problem set here, right, as I said, we'll focus on having a random variable, right, trying to break it down to sums, right, of simpler random variables. May or may not be indicator, right, but that's a theme. We'll work through a lot of problems at this time, right? So just be prepared. Okay, so let's start with the first one. Okay. And it's a coupon problem. It's number 42, right, in your textbook. Chapter 2. All right. Again, I'll let you read it and ask for the input, right? So the first question, of course, right, is how do you express it as a sum, right? What are the xi's? Those are always that's always the first question. All right. And so let's discuss this a little bit, right? Before we go to the main question. With each of these questions, right, it's highly advisable for you to visualize, right, the scenario that's being described in the question. I know that that's probably the last thing you want to do, maybe, for some students, because you just want to solve it and move on. But trust me, right, if you don't build up this habit of visualizing, right, what's going on, two things. First is you won't deeply appreciate why we solve the problems the way we do, and the solution may not make sense to you. Second, which is worse, is on the exam, you will not be able to tell which problem is which, right? Because it's just a bunch of symbols and things like that. But if you visualize it, right, when you read the problem again, the image, right, the meaning will come back and you recognize it, right? It's hard work, okay? I will acknowledge that. But that's the only way you can digest these things. Like you have to sit down, right? Read each problem carefully and say, do I kind of see what's going on here, right? Again, not in terms of the answers. No one knows the answer right away. Trust me on that. Do you see what I'm talking about? The image, right, of the process going on. And I said that word, right? Process. We're not dealing with stochastic process proper yet, but as you can see, right, there's already a random process going on. What is this random process? This random process, as you can see, right, is similar to a geometric random variable, except the goal is different, right? You have, right, independent trials, correct? Where each of the trial can have m outcome, right? So you just keep on, right, doing this. But then what's your goal, right? Your goal is you keep doing it until that time where you have all types present so far in your stream. Correct? And so you see, right? This is exactly a stochastic process, but we're not phrasing it exactly like that. So that's what I'm saying, right? We're moving toward that direction, right? Just preparing the tools to do so. Now, another question, right, we can ask, or like, is something that can be helpful. The questions asked here are always abstract like this. If possible, can you phrase it in a more familiar context? Like measures and things like that, right? Invent stories for yourself. So that, right? Because if the more familiar the experiment is, maybe the easier your brain will think about it. So this question is described in this kind of exotic way, right? Ish. Is there a familiar experiment that would match this, that we're more familiar with?
This seems like a negative binomial variable because we're looking for m successes in a way, but each type of success is different. Where
Right, but you're walking to dangerous territory here. Yes,
No.
you're right. It's like negative binomial, but it's still not quite, because right, the successes are different types. So,
Yeah.
I'm not saying that you're wrong, as long as you keep that word flavor, right? It has a flavor. I agree with you completely. But if you use the negative binomial as the inspiration here, I think that's dangerous. You know what? In fact, maybe you're not. Because you see here, right? In fact, the hint, right, says it's a sum of this, where each of them is a geometric random variable. The negative binomial, right, is a sum of geometric random variable. So who knows? Maybe your inspiration is good. So you're right, but keep in mind that these are different outcomes, right? So I'm not even asking at that high level yet. I'm asking for a very specific experiment that we can do that has this flavor. Maybe I have something too specific in mind that you guys cannot get, but any other input? Here's what I have in mind, right? And this is it. You can roll a dice, right? And corresponding to rolling a dice, M here will be 6. And you roll a dice until when? Until all 6 numbers come up. Right? That's exactly what this question is talking about. So if you put that from that point of view, right, this is actually quite hopefully a little bit more natural, right? You just keep rolling the dice until you have all 6 numbers comes up. On average, how long does it take you to use? Does that make sense? Okay, now having said that, right? Let x be the variable we need, and we need to express as a sum, right? They already say that. So what are the xi's?
Number of coupons collected till you see the ith type? Is my guess.
It's not specific enough, I'm afraid, but let's see. Number of coupons until the ith type, is it the same?
Or the number of additional coupons from the I-1th type till you see the ith type, maybe.
That's much better, right? That's much better. Exactly, right? It's not the ith type exactly, but the additional coupon. That word is exactly very good, right? Additional coupons from I-1, right? But having said that, it's not I exactly. You think about it, right? Let's take the rolling of the dice, right? Example as an example. You roll a dice, right? What will be the first number you see? Who knows, right? From 1 to 6. Let's say it's 5, right? And then what's the next number you see? Again, who knows, right? Could be a 2. Correct. And then the next number, right? So if you want to attach this I with the ith type, does that make sense? Then that might read a bit differently. Because, you know, in terms of the dice, the 6 type is number 6, correct? But this doesn't imply we must get the first one before we get the second one, right? Doesn't go that way. Do we understand? So basically, right? You roll, right? The first spot, you will get 1 time, right? Whatever that is, right? So you can call it first new type. And then you will need to roll again until you see the second new type. Do you see what I'm trying to say? So, right, let's say your first roll is a 6. Then, right, you might repeat a 6, who knows, until you see another one, let's say a 4. Right? In that sense, this is your x1. And this is your x2. And then, right, you might repeat until you see an x1. That's your x3. Do you understand? So xi is what? Xi is the number of conditional coupons. That's correct, right? Everything's correct. But we want to probably throw the word new type into it, because we don't want to refer to the original classification of the coupon type, right? This is new in terms of how it's coming in into the stream of collection. Are they okay? Any question here?
Is this
Right.
a version of like exponential? Like would this be something?
No, let's not go there. Because, okay, because you know, eventually many things are connected in some way, right? I could say yes, I could say no, but I want to say no here only because exponential is a continuous random variable, and we're dealing with discrete. So I just want to kind of put it there, right? There is some flavor of that. You're not wrong. I could feel it, but the connection is very subtle and delicate, right? It's not right there. And the most dangerous thing, if I say yes, you might think we're working in a continuous context, which we're not working in a discrete context, right? The only reason why there might be something to what you say is the geometric random variable actually is a discrete version of the exponential random variable. That's why you're seeing that kind of moment there.
Got it, that makes sense. Thank you.
All right, so if you understand what I'm describing, then notice, right, in the hint, they don't tell you, right? Notice, right, if you say it's a geometric, then what do we need to specify?
The probability of success.
Correct. So can you tell me, right, if I call xi in this type, right, if this is in my definition, then what is the success probability of xi?
One over the categories left, the number of them.
Excellent, excellent, right? So it's gonna be, for example, so. Right, so. Well, hold on, one over, I don't, wait, hold on, I think it's. Is it one over category left? No. That doesn't sound, is that right? Wait, hold on, let me see. Yeah, it sounds right, hold on, let me see. Is it? I'm confused. Hold on, let's see, right, let's use this, right? Because you have to be careful, for example. What is the distribution of x1? Let's work with that first. Let's work it out and then we'll see what the abstract answer is. What's the distribution of x1?
1/6? Like P
No.
equals 1/6? So you know,
No,
okay.
P equal 1.
exactly. X1 is p equals 1. Do you see? So x1 is just 1. Or it's just 1. Why? Because the first one is guaranteed to be new, right? Whatever that is. Does that make sense? So there's this peculiar edge case you want to start to work with to build it up. Right? X1 is 1. The first one is the new one. Correct? Now let's start with x2. X2 is what?
5/6.
Yeah, it's x2 is 5, 6, right? So it's not 1 over the remaining. Right? Do you see why x2 is 5, 6?
Yeah.
Could you explain?
Right? Because yeah, sure. Because right, if x1 is right, whatever, right, a number 6, right? Then when you get a new type, but what is the success here? Success here is to get something that's not of the old type. Yes, getting something that's not a 6 is a success.
Oh, this makes sense.
So that's why, right, we count from what's appeared so far, not what's remaining. All right. So can we see what the abstract number here is?
N minus parentheses I minus 1/n.
M, right? M
Sorry,
minus.
M. Yeah.
No, that's not the matter. They did call it M, but yeah, M minus. I minus 1. Perfect. Are we okay? Any question? All right, so right, once we identify that, everything else works. And of course, right, this sum has sort of like a reverse count, so to write like this is a bit more intuitive, right? A bit more nice, but notice that the logic goes the other way. Okay, any question about this problem? Okay. Let's look at the next one. So, some remark about this question. The first thing about, a lot about these problems, right, as you can see, is how you interpret the random variables, right? And notice the title of this textbook is, I think, something about introduction to stochastic modeling or something. Right, of course, stochastic process, right, is stochastic modeling, but notice, right, one thing that this book teaches you, right, that I would claim other textbook on stochastic process doesn't, and maybe, right, you like it, you'll be annoyed by this, the aspect of modeling, right? And modeling actually is a very important tool in math, because, you need to see what you want to denote. Okay, as a random variable, to get the math out correctly. And frankly speaking, right, that's what math is about. If you get the right idea, the right connection, then the calculation will kind of come to you. If you don't, then you can't, right? And with that kind of comment here, right, if you just kind of stop the question here, right, and forget the hint, because the hint by itself is a little bit peculiar. But if you just kind of, right, try to look at, the question by itself, right? Again, the question makes sense for whatever reason, right? I mean, at least you understand what the question is asking. But if you try to break it down, right, into some of other random variables, then I would argue, right, for this kind of question, right, probably it will take a while before you even hit on the right idea to begin with, right? But so, and that's why the hint is there, right? To tell you what the indicator function is, all right? But so let's kind of look at, right, the context here. So there, for, let's say, right, here, a way to, let's say, a good way to model, right, this scenario is to say that we have, right, balls that are labeled, let's say R1, R2, right, up to Rn, right, red, and B1, B2, right, up to Bm, right? And these are, let's say, mixed, right, in random sequence, right? Does it make sense? Something like that, right? But they're n plus m lined up. Okay. And you draw them one ball at a time, right? Without replacement. So you could think of like these are just marching out, right? They're just marching out. And you want to know the number of red balls removed before the first black ball is chosen. So, right, in the picture I'm drawing, right? So, of course, this is a random permutation, right? You can think of it like that. Here, right, of course, the number of red balls removed before the black ball is shown is 2, correct? Right? But then, right, you see, it's exactly, right, you see the way you count it, right? If you just kind of let this guy march out like that, right? It's like, you can think of this as a doors, right? Then you would look at the red balls, right? And you see exactly that, right? The ones that are taken before any black ball is chosen, exactly will be the number of red withdrawn before the first black. So my picture is just kind of like, re-illustrating, right, the idea of the question, of the problem. Any question here? But right, I mean here, right, they tell you the indicator function. But I just want to say, right, because notice, right, I just hopefully try to make you appreciate, right, the hint. Because notice, right, the labeling of the reds and the blacks like this, right, this picture is not that trivial to come into, right? Because for us, when we look at this urn, we could label it, we could visualize it, right, as non-labeled, meaning the R's are not distinguishable, the blacks are not distinguishable, right? That's a valid way to approach this, not approach, but to view the urn. But that would not be helpful in solving this question. So, right, this picture is helpful in solving this question. That's right. So, again, in math, right, the right picture is the key, right, to solving the question. But anyway, right, so I hope from part A, right, X is a sum of xi. I hope that's clear. Now, I go somewhere to where, at the risk of, asking a trivial question, see if you're following. I go somewhere to where,
I goes from 1 to n.
and Nick, right, yeah, correct, because number correct, that's correct.
It's the
Okay,
time
so,
index.
say again?
This is like the I comes from a time index, right? Like it's a time index.
I comes from the red. So
Okay, yeah.
basically, look at this, right? Look at my picture. Basically, you label the reds, right? You label the reds, so you distinguish the red, and this is exactly the thing that we're not used to when we look at an urn, because I think we're trained from probability theory, right? That if you look at an urn with n blacks, whatever n reds and n black, we kind of look at them as indistinguishable, right? It just makes the account easier. But here you want to distinguish them because of this kind of question being asked. That's exactly the, let's say, the conceptual difference that may or may not help to solve the problem. But yeah, it's just really the reds.
Quick
Okay,
question.
so go ahead.
So the wording without replacement implies there's some sort of dependent structure between the xi's, right?
Absolute, you know what? Yeah, I think so. Should be.
It probably isn't relevant to this question because we're looking at
Because you look at expectation, correct, but if you look at variance, absolutely. I'm trying to see how to phrase it that, yeah, for example, right, I mean, if the ith ball has been already withdrawn. The ith red ball, right, then it will affect how the red balls withdrawn before the black, right, I think so, because you reduce the number of balls in the urn total, right, yeah, I think so, they are not independent, I don't think so. Okay, so B, right, expectation of x is a sum of expectation of xi, right? Which is probability xi equals to 1, right? So these are routine, but they're not routine, right? Sorry, this is indicator function, but notice right here is not indicator function per se. But anyway, right? So, but then the last step, as I said, right, may or may not be trivial. So here, right, what is probability xi equals to? What do you think?
N over n plus m.
All right, I guess help me out here. The top is Mike or Nancy. Mike or Nancy on top.
Oh, it's n for red balls.
And for Nancy, right? Again, it doesn't matter. We'll look at whether it's right or wrong, but you mean Nancy or Mike? Nancy on top.
Yeah.
You want that, right? Okay, and m plus n, right? Okay. Again, right, this is your proposed answer. And we will ask you, right, how you come up with this answer, right? So what is your logic?
Because you're trying to pick the first red over the total number of n plus m balls.
Yeah, I mean, I think that's correct, right? If the answer is obvious to you, I think that's good, right? But I think again, who knows? Maybe let's just at the risk of asking or emphasizing the trivia, right? The answer here is not dependent on I, meaning doesn't depend on it's not dependent on the red ball. Is that clear to us that that's the case? That the answer here does not depend, it's not dependent on I, even though the xi's are dependent.
Can you elaborate, please?
Yeah, sure, right. It's actually the same logic as, let's say, the hat problem. Right, if you let xi be 1, if the ith person, right, gets the right hat, 0 otherwise, right? Then probability of xi equals to 1 is 1 over n, right? Even though the xi's are not independent, because the ith person, right, action has some influence on the j person's action. Right, this happens a lot in this kind of setup. The reason, right, why we kind of tend to confuse the two ideas like this, right, yes, xi and xj are not independent in both contexts. But when we look at something like this, p of xi equals to 1, right? What we're focusing on is only from the ith. Oh, and you know what? I think this answer may be wrong. Right? We'll see. But right, I'm not promising this answer is right yet. It could be. I have a vague feeling it's wrong. But right, but notice that when you look at p of xi equals to 1, you're only focusing on the point of view of the ith person, right? The ith, ignoring all other information. No further information allowed. Right? The reason why we tend to be confused on, why this is one over n and not something else, is when we think about the ith person's action, like picking his hat, we tend to build in the big picture where we say, oh, this person picks this person picks that, right? From the ith person's point of view, he knows nothing about that at all. He knows nothing, right? He just reached in and picked the hat, correct? And just to give you a demonstration, right? Suppose that you somehow know that the ith person is the last one to pick, right? You know what I mean? Like, let's say that people pick their hat out in sequence, right? Why not? Because let's not say that everyone just reached their hand at the same time and pick out at the same time. If the ith person pick the hat last, or it's not pick the hat, pick a hat last, does that change this probability? Does it change that number?
Yes.
No, right? No, and exactly. The reason is what? Even if that person is the last one to pick, he doesn't know, right, what the other person have picked. That's the crucial thing, right? So even if he's the last one to pick, he just pick it without knowing anything. And of course, from his knowledge, you see probability is a reflection of the information you have access to. His knowledge is just pick something randomly out of n hands, right? Because these people randomly leaving one hand to pick. That's right. So that's why it doesn't change it. So that's why here, right, this number is not dependent on that. Okay, because from the ith red ball's point of view, right, it doesn't care for what happens. It has no information about what happens to the other reds. I mean, it doesn't know if the other reds have been picked out before the black or not. It doesn't know that. Does that make sense? But when I say, right, I think this number may be wrong, right, is this. Put your point of view into the ith red ball, right? And what is your success? Your success, right, is that you think of you are taken out before the black ball is chosen. Right? So is that n or n plus n? Does it depend on n? So let's again, right, these questions are very subtle, so take our time, right? This is not something we just walk in and say, yeah, that's the answer. For example, right, let's imagine the scenario when there's 1,000 red, right, just to make it dramatic, and only one black. Okay. And I zoom in on a particular red, and that's when the probability is going to get picked up before the black. What do you think the answer is? If I have 1,000 reds and only one black, and I zoom in on one particular red, and that's what's the probability is get picked up before a black ball. What's the answer?
Could you think about it from a complement perspective by saying the probability that you're not choosing the one black? So,
No. Again, right? It's very important for us to get the picture clear. Notice the picture is that we agree, right, that the blacks and the reds are arranged right in a line, correct?
Mhm.
And then I march out, correct? The door, right? And we just look at until the first black is encountered, right? Because the first black is chosen, correct? Okay, now if that is still too abstract, right? Think about it like this, right? Let's say male and female, right? And take your pick, right? You guys in this class, and let's say males and females, right, are aligned, right, in a line. right? And they're walking out of the room. And let's say there are 999 males and 1 female, right? And you are one particular male in this room. And if you're female, maybe you can reverse the question, who knows? You're one particular male in this group.
I think your
What's the
screen
problem?
froze again.
Is it?
Oh, no, no,
Is
it's
it
good
from-
now. Yeah, it's good
Yeah,
now.
yeah. Right, if there are 999 males in the room, right, and 1 female and they're lined up randomly. And you're one particular male in this room. What's the problem you walk out before the female? Is it 999 over 1,000? I think, right, my arguments in that case, I think the problem is 1.5. You see that? Because, right, you are focusing on the particular position of 1 red ball only. And you're not looking at all other red balls. Right? And so if there's only 1 black, right? Then what's gonna happen? You either place before the black, whoever you are, or you place after the black, right? That's it. Right? Because it's all permutation, random permutation along the line. Do you understand?
Yes, that makes sense.
So that is tricky here, right? So what should the probability here be? It's not n over n plus n, but what should it be?
Generalizing what we just talked about with the m equals 1, I would guess that it's 1 over m plus 1. I mean, that's algebraic thought.
Right, but it's just think about it in terms of like, you know, it actually makes sense in terms of like logic too, right? You, right, you are one particular red. And you ask, right, what's the probability you will come out before all the m blacks? What's the probability?
Oh,
Probably
it's
is
1 over m plus 1. Yeah, that makes
Yeah.
sense.
Okay, right, so perspective, right, perspective is super important. So. Oh, wait. Let me see. Oh, I did not include the answer for this one for some reason. I would, right, but yeah, this is the answer. So n over m plus 1. I think this is time for today, so we'll continue with this problem set next time. I think Friday is 4th of July, right? So we won't have class. So I think Wednesday is the last day of class for this one. All right, any question before we stop here today? All right, have a good day, and I'll see you on Wednesday.
Thank you.
Thank you.
Thank you.
Sure.